Today we're going to be talking about equilibrium. When an object is in equilibrium, it's not moving and it's not rotating. It's just sitting there. So in order for something to be in equilibrium, there must be no net force on the object, because if there were a net force, the object would be accelerating. But even an object that's not accelerating, if it has no net force but it has a torque, then while its center of mass won't be accelerating, it will start rotating. So in order for something to be in equilibrium, the torque, the net torque on the object also has to equal 0. So that's basically equilibrium in a nutshell. If something's in equilibrium, the net force on it will be 0 and the net torque on it will be 0. Now let's work some problems using these principles. But before we work these problems, I want you to pay attention to some of the things that you should learn as we work these problems. First of all, we're going to learn that you can use more than one rotation axis. There's more than one possible axes we could choose, and sometimes we're going to use multiple on one problem. In equilibrium, the torque about any axis must be 0. And it turns out that some choices for the axis are more useful than others. For example, usually you want to try to choose an axis which makes things you don't know go away. Then your problem is simpler. How can you make it go away? Well, for example, if you choose an axis such that the lever arm is 0 for a particular force, if that force is acting right at the axis, then it will produce no torque and it won't show up in your equation. Or if the force is acting in a direction directly towards or away from an axis, then sine of theta is 0 and you won't get any contribution to the torque from that force. Also, we're going to learn that we can be clever. You can try little tricks, like instead of using RF sine theta to find the torque, we can use parallel distance, and we'll review that in a moment. Also, you can break forces up into their x and y components and find the torque due to each of those, and that can simplify things sometimes. So here's our first problem. A thin uniform board with a length of 3 meters and a mass of 2 kilograms is placed on top of 2 tall, narrow bricks with rounded tops. One of the bricks is 25 centimeters from one end of the board. The other is 50 centimeters from the other end. What is the force on each of these bricks? Will it be equal? Well, kind of my intuition says that the one that's closer to the middle is going to bear more of the weight, right? You probably notice this when you're helping someone carry things. The person close to the middle tends to do more, put in more effort. But let's actually see what the math tells us. So first of all, we know that for this board to be in equilibrium, it's not moving. Therefore, the net force acting on it is 0. So that means the force of the board, force due to brick 1 pushing up, plus the force due to brick 2 pushing up, must cancel the force due to gravity, mg, downward. But in addition to having, well, this doesn't, if we want to know the force on each board, this equation doesn't do it because it's got 2 unknowns in it. We need more information. And so now we're going to apply this other equilibrium condition that the net torque must be equal to 0. So let's label our diagram now. So here's gravity, and gravity's acting on the center of mass. Let's call the length of the board L. Let's call the distance from the end of the board to the pivot point on the brick, XA, and from the other end to the pivot point of the other brick, XB. And now we know that the torque due to each of these forces, the torque due to gravity, the torque due to brick A, and the torque due to brick B, must all add to 0. But about which axis? Well, it turns out that the net torque has to be 0 about any axis. We can choose whatever axis we want. Why don't we try the center of mass? So let's put our axis right to the center of mass of the board. So now, if we do that, the torque due to gravity is now 0 because gravity's acting right at the axis, which means it has no lever arm. The lever arm is 0, R is 0. So that torque goes away. And then we have the torque due to the brick on the left, brick A, and its lever arm is just L over 2 minus XA, right? It's this distance. And then we take that distance times FA. Sine of theta is 1 because the force is acting at 90 degrees from the lever arm. And then similarly over here, the torque due to brick B is just the force that brick B is pushing with times its lever arm, L over 2 minus XB. Notice the torque due to force A is negative and the one due to B is positive. So we have to choose a convention here. So I've decided to let a torque pointing out of the screen be positive and a torque going into the screen to be negative. All right, so then if we take R cross F, so here's R and here's the force of B is going up that way. R cross F, right-hand rule says it's out of the board. Whereas if we look at force A, R cross F is going to be into the screen. So it's negative. Anyway, there's our equation. Once again, it's one equation, it's got two unknowns. Maybe we could combine it with the force equation or something, but there's an easier way. Let's be smarter about which axis we choose. Let's try finding the torque about an axis that goes through the contact point of brick A. The great thing about that is there's two forces we don't know, but one of them is not going to produce torque. The force due to brick A is not going to produce a torque about that axis because its lever arm is 0. So when we add our torques together, torque due to gravity about A, plus the torque due to brick A, about axis at A, plus the torque due to brick B about the axis going through point A, has to add up to 0. Well, the torque due to gravity, the lever arm is just going to be this distance, L over 2 minus XA, and then force is mg. The angle is 90 degrees, so sine of theta is 1. But the sign of this force is, if we do R cross F, that gives us a torque into the screen, and so we'll call that negative. Right? Now the torque due to brick A is 0 because it has no lever arm. The force is being applied right at the axis, so that's just 0, and FA doesn't show up in our equation. And then the torque due to force B is just the distance from here to here, which is the length of the board minus XA minus XB, and then that's the lever arm, and then we multiply by the force, which is the force of brick B, and then once again, sine of theta is 1 because the lever arm and the force are at 90 degrees. Well, now, since force A is multiplied by 0, it drops out of the equation, and I've just got an equation with just force B and things that I know. So I can just solve it for force B. So right there, boom, I put my axis where force A is, and I get an equation for force B. Easy peasy. Now we need to find force A. Well, what we're going to do then is we'll put our axis down where force B is being applied so that it goes away. And then when I add up my torques about the axis going through the contact point of brick B, I get the torque due to gravity is the lever arm, which is L over 2 minus XB times mg, right? And once again, theta is 90 degrees, so there's no sine there. Sine of 90 degrees is 1. And if we take the lever arm crossed into gravity, we see the torque by the right-hand rule is going to be out of the screen, so that's positive. That's what we decided we were going to call positive. And then there's no torque due to force B, so we just have to worry about then the torque due to force A. Well, the torque due to force A has a lever arm which is L minus XA minus XB, and we multiply that by the force. The angle is 90 degrees, but notice if I do R cross F, I get a torque going into the screen, so we decided that's what we would call negative. And so once again, this whole thing has to equal 0. There's no force B. The only thing we don't know in this equation is force A, and so we can solve for force A. Now, let's look at our two solutions. Here's force A and here's force B. All right? First of all, notice what happens when you add them together. When we add them together, we get these two things. They have a common denominator. We can combine them. And when we do that, we find that we have this in the numerator and this in the denominator, and they cancel out, and we just get mg. So our solutions satisfy the force equation, right? That the net force is 0, that these two upward forces added together equal the gravitational force downward and cancel it out. So that's good. That's a good check to see if, what we got makes sense. Here's another thing we can do to try and see if it makes sense. What if XA was L over 2? In other words, what if brick A was right at the center of the board? Well, if brick A is exactly at the center of the board, then it can just balance the board by itself, and brick B doesn't have to do anything. Well, let's see what we get if we plug L over 2 in for XA. For force A, we get this right here, L minus L over 2, and the denominator becomes the same as this part of the numerator, and we're just left with mg. So as we expected, if XA is L over 2, then brick A is going to do it's going to have all of the force, and so the force is just equal to mg, whereas if we plug L over 2 in for XA in the force B equation, we get 0. So it seems like the solution we found does what we expected to do, so probably it's the right solution. Let's plug numbers in. If we plug in all the numbers, we find that force A is 8.72 newtons, and force B is 10.9 newtons. And that's what we expected, right? We said the brick B is closer to the center. We expect that it's going to carry more weight. It's going to exert a greater force than force A. All right? Okay, here's another problem. A bar with a mass of 150 grams and a length of 15 centimeters is centered on top of a knife edge. An unknown weight is hung from the bar a distance of 7 centimeters from the knife edge. A weight with a mass of 200 grams placed precisely 3.5 centimeters from the knife's edge on the other side causes the beam to balance. What is the unknown mass? So this is how a beam balance works. This is how you can weigh things even though maybe you have a finite set of masses to compare it with. You can change lever arms. So, what axis do we want to choose? Well, here are our forces. I've got the mass on the left, which is what we're trying to find, and it's got a force due to gravity. The mass on the right is the known mass, and gravity pulls on it. The bar itself has some mass, and since the bar is centered on the knife edge, on the pivot, we can pretend like all of its mass is right there pushing downward. And then the knife edge is going to push the whole thing up. And we know, once again, if this is an equilibrium, the sum of the forces has to equal 0. That means that the pivot pushes upward with a force, which is the sum of the other forces, but in the opposite direction. So that tells us about the force due to the pivot. Now, an obvious choice for our axis is one right along the knife edge. Why? Well, first of all, the knife edge force won't produce a torque about that axis. Neither will the bar, right? The force of gravity on the bar is right at that point, so it won't produce any torque. And then we're just left with the torque due to mass on the left and the torque due to the mass on the right. And that's exactly what we're trying to find. We're trying to find the mass on the left given the mass on the right. And so since we don't have to worry about the knife edge of the bar, then the total equation is the magnitude of the torque on the left has to equal the magnitude of the torque on the right, and they have to have opposite directions, and so they'll cancel out. And they will have opposite directions, right? Because R cross F on the left is going to be pointing out of the screen, and R cross F for the right mass is going to be pointing into the screen. So the magnitude of the torque on the left is just M times G times the lever arm, right? And once again, the force is at 90 degrees from the lever arm, so we don't have a sine of theta. The sine of theta is just 1. And then similarly, on the right, it's just going to be the mass of the right mass times gravity times the lever arm, which, right, we know. And so then we just have to solve this for the mass on the left, and that was a very simple equation. I did a lot of talking, very little math. Then we plug in the numbers and we find that the unknown mass is 0.1 kilograms or 100 grams. Now, we could have chosen a different axis and still worked the problem, but it's going to be harder, all right? We initially chose a smart choice for the axis and the problem was easy. If we choose the axis right here about mass 2, then, or mass on the right, then we're going to have a harder job, right? Well, first of all, the torque due to this mass is going to cancel out. So you'd think, oh, well, mass 2 is going to come out of the equation, except we know that mass 2 affects the force on the knife edge, right? We got that from the net force equals 0 assumption. So here we are, the force due to the left mass plus the force due to the knife, torque due to the force of the knife edge, and the torque due to the gravity acting on the bar has to add up to 0, right? And then we don't worry about the torque due to mass right because it's right at the axis. It's being applied right at the axis. Well, the lever arm for the left bar is R left plus R right, okay? And the direction of the torque, if I do, here's R cross F, that's going to be positive out of the screen. The torque to the knife edge, all right? It's magnitude, right? The magnitude of the force is the sum of the masses times G, and the lever arm is just this distance here, R right, okay? And if I do R cross F, the right-hand rule says that's going to be into the screen, so that's a negative torque. And then the weight of the bar, all right? So if we take the mass of the bar times gravity, that's this force here, and the lever arm is just R right, and if we take R cross F, that's out of the screen, so that's positive. And then we have kind of a soupy equation. It turns out that this term cancels with that, and then this term cancels with that one, and we basically get the same equation we had before. It's a few more steps. Not too bad. It wasn't as good a choice of an axis, but we were still able to get our answer. Before we work our next problem, let's review the idea of parallel distance. So imagine I have an axis here, a pivot or an axis, and I want to find the torque due to a force applied right here. Well, the torque is just the lever arm crossed into the force. It's just R cross F. The magnitude of the torque is RF sine theta, and of course, by the right-hand rule, the torque would be pointing out of the screen. All right, but notice this. What I'm going to do is I'm going to extend the force line, and then I'm going to draw a line from the pivot to that force line such that it is perpendicular to the force line. All right? This yellow line I'm going to call R perpendicular. It's the perpendicular. I said parallel up here. Shame. Perpendicular distance, not parallel distance. Complete opposite. So, yeah, anyway, ignore parallel. Perpendicular distance, perpendicular distance. So the perpendicular distance right there is in yellow. Well, note, if this is theta, this is also theta, which means our perpendicular's length is R sine theta. Well, R sine theta, that's exactly what goes up into our torque equation. So I can find the magnitude of the torque by calculating RF sine theta, but I can also just find the perpendicular distance, and then the torque is R perpendicular times force. I can't believe I wrote parallel. Perpendicular. Okay, so now let's do this problem here. A sign with a width of 20 centimeters, a height of 10 centimeters, and a mass of 0.5 kilograms is held up by two thin ropes. The left rope makes an angle of 20 degrees to the vertical, and the right one makes an angle of theta r to the vertical. What must the tension in each rope and theta r be for the sign to remain motionless? Well, let's do our diagram. All right, so here's a vertical line. So this angle here is theta left, and this angle here is theta right. The tension in the rope, the force due to the rope on the left, I'm going to call tension left, and the one on the right, I'm going to call tension right. So there's two forces. There's one more force. There's gravity, mg, going downward, and we pretend that all of the mass is at the center of mass, right? The effect of gravity is as if it's just pulling right on the center of mass. Let's call the height of the sign h and the width w. Okay, so our objective is we want to find the force due to the two ropes, tension left and tension right, and the angle of the rope on the right. We're given the weight of the sign, the height, W is the width. We're given the width of the sign, the height of the sign, the mass of the sign, and theta L, the angle of the rope on the left. Okay, our basic equations are the net force has to equal 0. If the net force is not 0, it's going to accelerate. It won't be in equilibrium. And the net torque on the sign about any axis has to be 0. So first let's do the forces, and let's break the net force up into y components. So the y components of force are tension on the left, cosine theta left, plus the tension in rope right times cosine theta right, and then gravity, mg, downward. So that has to add up to 0. In the x direction, the gravity has no x component, but the left rope pulls to the left with a force tension left sine theta, and the rope on the right pulls to the right in the positive x direction with a force tension rope sine theta r. So there are my equations for the force. Now the torque. And once again, which axis are we going to choose? Well, let's start with an axis through the center of mass. This is an obvious choice, but not usually the best choice, and you're going to see why. Well, the torque due to gravity is 0 if our axis is through the center of mass, because that's where gravity's acting. There's no lever arm. Why is that a bad thing? Well, gravity's one of the things we knew. It's not one of the things we're trying to find. We're throwing out information, right? Also, the torques due to the tension of the ropes have complicated lever arms. So torque is R cross F. The magnitude of force of torque is RF sine of theta, some angle. But what's that angle? Well, let's look here. For the rope on the right, there's our lever arm. If we extend the lever arm out, R cross F is that angle right there. What is that angle? It's not theta R. It's not 90 minus theta R. It's more complicated. Well, maybe we can use the perpendicular distance, not parallel distance, perpendicular distance instead of R sine theta. Well, let's extend the direction of the force down here. We draw a perpendicular line, and what's that length right there? It's not obvious right away. We'll have to do some trig to get that. So, yeah, it's a complicated one to use. Plus, it gets rid of gravity, which we kind of wanted. We need. All right, but if we're clever, we can make it a little bit simpler. We can note that we can break up the torque due to each of these tensions into a torque due to the x component of the tension and the y component of tension. So the torque due to the left rope is just going to be the torque due to the x component of the left rope's force plus the torque due to the y component of the left rope's force. All right, so to find the x component, we're going to say, well, look, here the x component of the force is in this direction, and the perpendicular distance then is just that line right there. And that's simple. That length is just h over 2, and the angle between the perpendicular, we don't need to know the angle if we're using perpendicular distance. So there we go. The torque due to the x component of the left rope's force is negative torque left sine theta. All right, torque left sine theta, L. That's the x component of the force due to the tension of the string. So tension left sine theta, and then we multiply by the perpendicular distance. So instead of doing r sine theta, we're just going to do r perpendicular, and r perpendicular is h over 2. And notice if I do r, here's r cross f, I'm going to get torque into the screen, so that's negative. Similarly, for the y component, the torque due to the y component of the tension in the rope on the left side, we can just say, well, look, here's the y component of force. We extend that down. We find the perpendicular distance to the axis. And then we just say, oh, the torque due to the y component of the rope on the left is the tension in the rope times cosine of theta L. That is the y component of force. And then we multiply by the perpendicular distance, which is W over 2. And so then we just add them together, and there is the torque due to the rope on the left. That seems like too much work, right? We're going to find a better way to work this. But just for now, let's keep going. On the right-hand side, we can do similar things and find the torque due to the rope on the right. We know that the sum of those two torques has to equal 0 because there's only 3 forces, and gravity has no torque about the center, about that axis, about the center of mass. So if we put those together, we've got an equation. It's got 2 unknowns. It's kind of messy. And let's stop right there and choose a better axis and see how much better the problem gets. Let's start with an axis going through the right rope contact point. So the point where the rope makes contact with the sign, let's take an axis going through there, coming out of the screen. Okay, why is that a good choice? Well, it eliminates 2 of the unknowns, theta r and tension R. So we're only going to be left with one unknown, which is a tension in the left rope. So let's figure out the torque of all of our forces about that point. Of course, the torque due to the rope on the right will be 0 because the axis passes right through that contact point. All right, so remember, torque is R cross F. We can also find the magnitude of torque by saying RF sine of whatever the angle is between R and F. Or we can just find it by finding the perpendicular distance times the force. All right, so the torque due to gravity is just W over 2 mg. Why is that? Well, look, here's R. Here's the lever arm going from the axis to the center of mass where gravity is acting. If we extend the force due to gravity, we can draw a perpendicular line, a line from the axis, which is perpendicular to that extended force line. And that's our perpendicular distance right there. It's just W over 2. So torque due to gravity was easy. Now let's find the torque due to the left string about this point over here. There's the lever arm. The lever arm is just W, right? So the torque is just going to be W times tension in the left rope times sine of, this is the angle, right? If we do R cross F, that's the angle right there. So it's the magnitude of the force is W tension sine of this angle, and this angle is 90 degrees minus theta left. And notice the torque will be negative. If I do R cross F, the torque by the right-hand rule will be into the screen, which is what we call negative torque, all right? Also notice that sine of 90 degrees minus an angle is the same as the cosine of that angle. So there's the torque due to the left rope, yeah? So then we just take that and we say, look, the sum of the torques has to equal 0. So we take the torque we found earlier due to gravity about this axis, and then we add the torque we found for the left rope. The right rope has no torque, so these two add to 0. We just have to solve this, and we get the the tension in the left rope. It's solved. In order for the sign to not rotate, this is what the tension in the left rope has to be. We found it. Now to find the right rope, we've got it. Let's plug in the numbers. We plug it in, and there is the tension in the left rope. Now to find the right rope's tension, we just choose a pivot point at the point of contact for the left rope. And in that case, there will be no tension from the left rope. There will be tension. There will be no torque due to the tension in the left rope because there's no lever arm. The lever arm is 0. The torque we can find the torque due to gravity, right? Torque is R cross F, or R sine F sine of the angle between the lever arm and the force. Or we can find the magnitude of the torque as just the perpendicular distance times the force. So for gravity, this time it's negative W over 2 mg. All right, if our axis is right here, there's the lever arm, there's gravity. If I do R cross F, I know I'm going to get a torque into the screen, so that's why the torque is negative. What's the magnitude of it? Well, once again, we extend the gravity line up, and then we draw a line that goes from the axis that hits this line, our extended force line, at a 90-degree angle. And that length right there is R perpendicular, which is just W over 2. So there's the torque due to gravity about the axis running through this point right there. Okay, now since there's no torque due to the rope on the left, we just need to find the torque due to the rope on the right. Well, its lever arm is just going to be W. And so if we extend that out, here's the angle, R cross F is right there. So first of all, right-hand rule says it's going to be out of the screen, so a positive torque. And the angle is that angle right there, which is 90 degrees minus theta R. So the torque from the right rope about this axis is just W, the width of the sign, times the tension of the rope, times the sine of that angle right there, which is 90 degrees minus theta R. But sine of 90 degrees minus an angle is just cosine of the angle. So there is the torque due to the rope on the right. And then we just say, well, that plus the torque due to gravity has to add up to 0. I solve that, and I get the tension in the right rope. Except I don't know theta R. We'll hold off for a minute. So here are the two, getting ahead of myself. Here are the two tensions that we found. Now we have to also obey the force equals 0 equations, right? Remember we found these earlier, that this is the y component of the net force, that has to be equal to 0, and the x component of the net force has to equal 0 as well. Well, I'm going to take these solutions we found, and plug them in for tension left and tension right. And when I do that, notice that the cosines cancel out, and I'm just left with mg over 2 plus mg over 2 minus mg equals 0, and that works. So our solutions that we found are, they work with the y component of force being 0. They satisfy that. So now let's look at the x component of force. I'm going to plug these tensions we found into the x component of force equation, and what we find is this. We plug these in, and we get this equation. And notice that m and g, I can divide by m and g, I can multiply by 2 and get rid of all of that. And what I'm left with is sine theta L over cosine theta L negative, plus sine of theta r over cosine of theta r. Sine over cosine is just tangent, right? So negative tangent theta left plus tangent theta right equals 0. So in order for there not to be any force in the x direction, those two angles have to be equal. Theta right has to equal theta left, which is equal to 20 degrees. So there's one of the 3 things we needed. Now, knowing that, I can plug my numbers in to find the tension, and I find that tension left equals tension right equals 2.61 newtons. And there are my answers. So I got it. Now you might say, well, wait a minute. Is it possible that theta right could be something other than theta left and their tangents still equal? Well, here's a plot. Here's in blue, I have the tangent of theta, and here is the red line is the tangent of, tangent of theta is a function of theta, and here the red line is the value that you get when you take the tangent of 20 degrees, theta left. And you see that they intersect at, theta right equals theta left. They both equal 20 degrees, but they also intersect at 200 degrees. So maybe that's an answer. Well, if we draw that, that would have the rope going this way, and then the torque's going the wrong direction. And as you can see, right, I'm torquing this way, torquing that way. If I look at the torque about the center of mass, this one's going to be a torque into the screen, this one's going to be a torque into the screen, and we don't satisfy things. We implicitly made some assumptions about the direction of the rope, so that's not a possibility. So our answer is just theta right has to equal theta left, and both of the tensions have to be the same. Otherwise, the sign will not be in equilibrium, and it'll start to move or start to rotate, or both. Okay, what did we learn working these example problems? Again, we learned that you can use more than one rotation axis. In equilibrium, the torque about any axis must be 0. And so you can choose which axis you want, and oftentimes working one problem, we will use multiple axes to get multiple equations with different pieces of information in the simplest form. Now, some choices of axis are more useful than others. So we try to choose an axis which makes things we don't know go away, right? And you can be clever. Remember, we did some clever things, like instead of trying to find sine of theta, we used parallel distances. So to find the magnitude of torque, instead of using RF sine theta, we just said R perpendicular times force to get the magnitude of theta. Also, at one point we said, look, I can break a force up into X and Y components, and then I found the torque due to that force by finding the torque due to the X component and the torque due to the Y component and adding them together. So there's different tricks you can use with these types of problems. Well, that is the end of our discussion on equilibrium, and very soon we're going to get on to more exciting problems like things that aren't sitting still, like objects that oscillate. All right, we'll see you next time.